We're going to check on a couple more things. We'll be right back with you. Please mute it.
Hey Luke, you are presenter now, so you should have an option to enable your webcam and your microphone up top.
I can see Ramiro and hear people speaking.
Hey Luke, you want to go ahead and do a sound check real quick?
Okay, Janet can hear us.
It's just if you open my mic, let me know. Hello, Luke. Let's do a sound check really quickly. Can you hear me okay? Okay, I see your lips moving, but I'm not getting any sound from you.
No, nothing yet, Luke.
Speakerphone, microphone. It's not ideal.
It probably works.
Yeah.
Luke, if you look at the top of the web browser, you should see a microphone. If you click on the little drop-down box, microphone, and you should get a little dialog box asking for permission to allow.
We're just missing a few key pieces.
I'll leave the mic.
Thank you all for being patient as we're working through a few technical difficulties here at the beginning. Making some arrangements to overcome these, and we should get started in just a few moments.
Okay, so Luke, we're going old school, and I'm sending you the number, everyone will see it, but just ask these
Ready
if
to
you're
go?
ready to dial.
Yeah, we're good to go, so we'll.
Okay, well, good afternoon, everyone. We're glad to have you here today for the Explore Marvel Moon Growing Up Moon webinar. We've been working out just a few difficulties here, and so before I really get going, I just want to let Luke know that we're going to be sending him a number to call into, and we will get his audio up and going through the phone. So Stephanie will be sending you some information shortly via the chat, and while they're working on that, we're going to go ahead and get going with our webinar today. Again, I apologize that it has been a little bit delayed in getting started today. I hope that you'll still be able to stick with us through it to the end. Okay, so welcome. My name is Eve Halligan, and I am an Education and Public Outreach Specialist at the Lunar and Planetary Institute in Houston. And it's a great place to work. I get to help share the amazing NASA discoveries and mission research that comes out regularly. And bring it to the educators, you, so that you can use it and help educate the public and the children in your libraries. So with me today, I of course won't be alone. I have some help here, both will be in front of the camera and behind the scenes. And I'd like to take a moment to just introduce them to you. Along with me today, I'll have Dr. Stephanie Ship. She is the manager of our education group here at the Lunar and Planetary Institute. And she'll be helping to keep an eye on the chat and to help pass along your comments and your questions as we're going through the webinar today. I also have with me Andy Shaner. And Andy is an education and public outreach specialist like me here at the Lunar Planetary Institute. And he's going to be helping me to demonstrate and then to help lead some activities that we'll be going through in just a little while. Also have some support through our computer center. We have Ramiro Padilla here with us today, and he will be helping on the technical end. So if you do have issues, please use that chat box. He will work quickly to try to help resolve those issues with you. And we also have Yolanda Ballard here with us today. She will be behind the scenes helping with our materials and our technical support as well. And finally, last but not least, I am very happy to say that we have Dr. Luke Downs with us here today. He's going to be spending some time talking with you about the science and the research related to the moon. So before we get to Luke's talk, I have a few things that I'd like to share with you. And actually, the first thing I wanted to go over really quickly has to do with our webinar platform today. Many of you may not have used Adobe Connect before, so quickly I just wanted to orient you. And if you look, you probably noticed the chat box. We would ask that if you have comments or questions during the majority of the webinar, that you would use the chat box. Above that, we have the attendee list. You'll notice your name there along with everyone else's. And if there's a microphone next to your name, it means that your mic is on. So we want to make sure that you stay muted when you're not speaking so that we don't get disruptive background noise. So take a look at that. Make sure that your microphone is muted unless you will be speaking, and that way we won't have those kind of background noises going on. Also, at the top of the bar on the right, there's an icon that looks like a person holding their hand up, and If you click on the arrow next to that, you'll be able to raise your hand if you would like to say something with your microphone, and that'll allow us to open up your mic and give you a chance to talk with us. Now, for the greater part of the webinar, we would ask that you stay muted and that you use the chat box to communicate with us. However, we do want to hear from you, and we want to hear what you have to say and your questions. So towards the end of the webinar, we will have a section where we will open up the mics, and we will remember to use that raise hand function. And we'll give you all a chance to have an interactive programming discussion for how we can use these materials and any other questions or comments that you may want to share at that time. So just a quick few tips then for using the webinar, and hopefully that'll all go smoothly for all of us today. So next, I'd like to just give you a quick little overview about the Explore program. Some of you may be familiar with Explore and some may be new. Explore is a program that's NASA supported. It's designed to engage children in space and planetary science in the library. So the materials we'll be going through today were designed and created specifically for use in the library setting. And of course, these materials are free, which is great, and they're very hands-on and flexible. So you'll be able to use them in your summer reading programs, in after-school programs or festivals. You may also use them in science days or family events, whatever venue that would work for your facility or your organization. And so in order to access these, like I mentioned, they are free, and they're all available online at the Explore website, which is listed here. And so you'll notice we've gone to the Marvel Moon homepage, and you would normally find that along the left-hand navigation side with the topics right there. If you click on topics, you'll see all of the different topics that we have Explore educational materials for. And you can go to the topic that you're interested in. So you would find Marvel Moon, go there, and get the page we see before us. And here you'll find the activity descriptions, the setup, the directions for conducting and facilitating what we'll be looking at with the module today. You also find good facilitator background information. There are also other resources that may be very useful in your programs. If you also notice along the left side there underneath the topics, you can also find a calendar of events and upcoming opportunities on our website, as well as a discussion board that may be changing here in the near future, but provides some science, mission, and news from NASA that relate to the different topics within Explore. And we also tend to list our opportunities that are coming up for the Explore program, such as the webinar that you're attending today. So please make sure to take some time and go visit our site, browse around, and see what other topics you may be interested in. And as always, if you need to contact us, that information is there as well. And we're always happy to work with you to help bring Explore to your programs. Okay, so for today, we're going to be taking a look at the Marvel Moon Explore educational module. And so for the webinar today, we're focusing on a set of activities from that module that have to do with the formation and evolution of our moon. And here you'll see some wonderful comic pages, and these are from the Marvel Moon module. One of the supplements that goes along with the activities are these comic book pages, and they help to support the activities as the children are doing them. Also, you'll notice on the one towards the lower right, we also have featured scientists and researchers that are involved in lunar science. One of them is Luke Dones, who's joining us today, which is wonderful to have the comic character in life form with us. It must be a wonderful experience to be a comic book character. We'll have to see what he thinks about that in just a little bit. But again, this is a wonderful supplement to go along with the hands-on activities that we'll be conducting here in just a little while. Okay, so before I bring on Luke to talk about the formation and evolution of the moon, I wanted to just check in with you, and kind of check in with your homework a little bit. So here's the moon that we all know and love. And before the webinar, we sent you a homework assignment to get out and go look at the moon. And I also sent you a worksheet that was the Earth-based tour of the moon, which would help you to locate some different features on the moon. So in just a moment, we're going to put up a poll here, and we want to find out how many of you were able to do the homework, how many of you were able to get out and look at the moon over the past week. So here's the poll. If you could please vote and we'll see how many of us were able to get out and do it. Don't worry, this is not graded. If you weren't able to see the moon over the past week, we understand. But we hope at least some of you were able to get out and do some sightseeing on the moon. Okay, we're getting some results in. Let's see. Looks like we got at least about 76% of us were able to get out and look at the moon over the last week. So bravo, excellent, way to go. Hopefully you enjoyed that. And when you look at the moon, what is it that we tend to think about? Do you ever look at the moon and wonder, how did it get there? Well, that's the first question that we want to start thinking about here today. And how did it get to the way that it looks? So I'm going to have Andy come and help me here in just a moment. And if you were able to collect the materials from the list that I sent you, I would like you to grab your Play-Doh right now. You should have 2 different colors of Play-Doh. And I'd like you to start thinking about how the moon formed. How do you think it formed? And take your Play-Doh and start playing with it and try to model how you think that happened. I'm going to give you a moment to try that out. We're going to flip over to Andy here in just a moment. And then once you've played with it, we're going to take some of your ideas and model a few of them. Okay, so we've switched our camera over. Andy is preparing some Play-Doh. And I would now like you to start sharing some of your ideas. How do you think the moon formed? So go ahead and start adding those in the chat box. And we're going to pick just a few of them to model with our Play-Doh underneath our camera. Nope. Okay, someone's having a hard time hearing. We're trying out the Play-Doh and trying to use it to model how you think the moon formed. Okay, so Andy's going to put some Play-Doh under the camera now. I'm hoping we'll get some of your ideas coming in, so please share some ideas. So I see one that says, I had a small core and I'm adding the other Play-Doh to form a crust. Okay, Andy can try to show that for us. Let's see, we'll take a small piece of Play-Doh for a core. And she said she added some more to make a crust. Okay, so he's kind of putting pieces on the outside to make a crust. Any other ideas that you would like to share, please? Okay, so we have an idea that maybe the moon, broke off from another planetary object and then was captured within the Earth's gravitational pull. Okay, so let's see. Let's put an Earth in there. That'll be our green Play-Doh. And we'll see another planet here. A piece of it will break off. And we'll now get caught in the Earth's gravitational pull and start orbiting the Earth. Okay. Excellent. So now that we've got our brains thinking about how the moon formed, I'm not going to answer that question yet for you. But the next thing we would like to do is actually welcome our special guest today, Dr. Luke Dones. Luke comes to us from the Southwest Research Institute in Boulder, Colorado. and he's been there since 1999. He's also a member of the Cassini spacecraft imaging team, which is currently studying Saturn. And his research interests are the impact history of the solar system, the dynamics of comets and asteroids, and we're interested to see what he has to tell us now as far as his research. So we'd like to welcome Luke. He's going to be telling us more about the formation and evolution of the moon. Welcome, Luke.
Thank you. Can you hear me okay? Can you hear me okay?
I can hear you. Let's see what we got coming in here.
Okay. Okay, cool. Does the volume sound seem reasonable?
We're getting yeses.
Okay, all right. I'm not very loud spoken, but I'll do my best. Okay, so it's a great pleasure to be speaking with you all. I wish I looked as cool as my cartoon character, but you know, maybe if I do this again, I'll dress up. But anyway, this picture on the first view graph is a lunar orbiter photo of Copernicus crater on the moon, which is about 100 kilometers across. Lunar orbiter was one of the missions, the unmanned missions that were sent to the moon in preparation for the Apollo landings. And so, you know, I come from that era. I was 11 when Apollo 11 landed on the moon, and I have to say it's a great disappointment to me that we haven't sent people to the moon for 40 years. I mean, most people on Earth today don't remember the moon landings, and that's sad to me. And I hope I will convince you that the moon is still an interesting place. Okay, so let's see. So let me see. How do I do this? All right.
On the bottom left-hand corner, you should see little arrows. Okay.
I do see little arrows. Okay, there we go. Okay. Okay, so this is a picture of the moon, you know, taken not with a big astronomical telescope, but actually with by an amateur in Alabama. So, you know, you can see that even, you know, with a fairly modest telescope, you can get a really nice picture of the moon. And let's see, let me find my arrow here. Do you see the arrow?
Yes, we see the
Anyway, the thing I'm pointing to is Copernicus crater, which is the object you saw in the previous image, the lunar orbiter image. And I'd say there's also a Tycho crater down here. And these are two of the more recent big craters on the moon. Tycho is thought to be of order 100 million years old, and Copernicus about 1 billion years old. And that's considered recent by solar system standards because the sun and the planets are thought to have formed 4.5 to 4.6 billion years ago. So I think the main things you can see in this are that, you know, first of all, some areas are brighter than others. The bright areas are called highlands. The dark areas are called maria, meaning seas in Latin, because they look like oceans, although they're not, of course. They turn out to be lava, but we'll get to that later. The other thing you can probably see is that for some of these recent craters like Tycho and Copernicus, you can see these features called rays, which actually go quite a ways from the crater, and that's believed to be debris that's scattered a long way across the moon during impacts. Okay, so I'm going to try to tell you our current theory of how the moon formed, but what are we trying to explain? So this summarizes some of the major facts over here. The main thing, probably the biggest takeaway here as far as the composition, is that the moon the moon is made of rock, but it doesn't have a lot of metal in it. there is some iron. It has a small iron core, but overall it has a lot less iron and other metals than the Earth does, or the other terrestrial planets, the other rocky planets. In fact, the chemical composition of the moon is quite similar to that of the upper parts of the Earth, the crust and the mantle, although there are differences in detail. For instance, the moon contains less volatiles, meaning, notably water, but also other things such as sulfur. And then there's some things about the orbit of the moon and its size and so forth, which I won't go into right now. I just wanted to point out that, sorry, I keep using my cursor on my laptop and forgetting to use the arrow here. These 6 crosses indicate the positions of the Apollo landing. So here's Apollo 11, the first, and Apollo 17, the last. And you can see that they're all confined to a pretty small area of the near side of the moon. Basically only one side of the moon. We only see one face of the moon, although it wobbles a little bit, so we can see a little bit of the regions beyond the edge at times, depending on, when you're looking at it. But anyway, my point is that we really only explored with Apollo kind of the near side of the moon and only a relatively small part of it, kind of near the equator, roughly. So that right there is one reason that going back to the moon at some point in the future would be useful, that we really only have sampled a very small part of the moon. And as you'll see in a movie that we're going to show in a minute, the far side of the moon is actually quite different from the near side. Okay, so now I believe this is set up. It turns out that 3 years ago, a mission called Lunar Reconnaissance Orbiter, or LRO, went into orbit around the moon, and it has returned some spectacular data on the moon, images, altitude data, and other things. And so Goddard Space Flight Center, NASA Goddard, made a really nice movie summarizing the evolution of the moon and showing some of the things that LRO has found. So we're now going to show the movie.
From year to year, the moon never seems to change. Craters and other formations appear to be permanent now, but the moon didn't always look like this. Thanks to NASA's Lunar Reconnaissance Orbiter, we now have a better look at some of the moon's history. The moon likely started its life as a giant ball of magma formed from the remains of an impact on Earth about 4.5 billion years ago. After the hot material collected into a sphere, the magma began to cool, eventually forming a crust on the surface of the moon with the magma just underneath. Around 4.3 billion years ago, a giant impact battered the moon's south pole, forming the South Pole Aitken Basin and sending debris as far as the opposite side of the moon. This impact marked the beginning of a period that would cause large-scale changes to the moon's surface. One by one, more huge collisions shaped the terrain, some forming large basins that would eventually fill in to become the dark-colored patches of the moon, known as maria. They began as normal craters, but soon started to change due to the size of the impact on the relatively thin crust. Because the moon had not yet fully cooled on the inside, lava began to seep out through the cracks caused by the impacts. The resulting volcanic activity spread lava throughout the craters, gradually filling them in and cooling. Because of the high iron content of the basalt in the rock, the maria reflect less light and therefore appear darker than the surrounding highlands of the moon. Around 1 billion years ago, volcanic activity ended on the near side of the moon as the last of the large impacts made their mark on the surface. The moon continued to be battered by other impactors, although they were much smaller than the objects that formed the largest basins. Some of the largest, most recent, and best-known impacts from this period include the Tycho, Copernicus, and Aristarchus craters, which are unique due to the complex system of rays that stretch out from the impact site. Finally, we arrive at the moon that we see today. Though the surface continues to be affected by impacts, the rate has slowed down drastically to the point where the moon appears unchanging to the human eye. as a permanent record of its own history and a glimpse of how craters may have formed here on Earth. To nearly everyone, the moon appears to be a sterile, gray, unchanging world. But while the moon has remained largely unchanged during human history, our own understanding of it has evolved dramatically. Thanks to new observations, we now have not only unprecedented views of its surface, but a whole new tour of the moon that shows how both it and other rocky planets in our solar system have been shaped over billions of years. We'll start with one of the largest impacts, Oriental Basin, a feature that's as wide as the distance from New York City to Cincinnati. Using new elevation measurements, we can clearly see the effects of what is likely the last giant impact event in lunar history, with its outer mountain rings rising many kilometers above the lowest points inside the crater. The interiors of some craters in the moon's polar regions, like Shackleton, haven't seen sunlight in over 2 billion years. However, new measurements have created our best yet maps of these types of craters, allowing us to see deep into the shadows of this surprisingly young-looking impact crater in the south that's more than twice as deep as the Grand Canyon. Some impacts are invisible for other reasons. Although the ancient South Pole Aitken Basin is difficult to see from orbit because it is so large, new LRO topography maps reveal the largest impact basin in the Earth-Moon system, measuring several kilometers in depth and around 2,500 kilometers in diameter. Only the Hellas Basin on Mars rivals it in size. One of the youngest large-scale impacts on the Moon is the Tycho crater. This fresh crater may have formed only 108 million years ago, when dinosaurs roamed the Earth. We now also have an extreme close-up view of the crater's central peak, revealing a mountain with sharp edges, building-sized rocks, and a central boulder about the size of a baseball stadium. The Aristarchus Plateau is another recent lunar formation that has long interested scientists and astronomers. The crater itself formed in the same era as the Tycho crater, and what appear to be snaking river valleys were actually carved by ancient lava flows. Next, we arrive at Mare Serenitatis on the near side of the Moon. In December of 1972, the crew of Apollo 17 landed in the Taurus Littrow Valley, marking the last time humans have visited the surface of the Moon. With images from LRO's narrow-angle camera, we can clearly see the evidence of that visit. In this image, you can easily see the base of the lunar lander, along with the lunar rover, parked far from the blastoff zone. You can also clearly see the astronaut trails and the wheel tracks left on the lunar surface. We now head to the far side of the Moon, which cannot be seen from Earth. Our first stop is the Compton-Belkovich region, which shows evidence for young volcanic activity in the far side highlands. This feature is unique not only because it is isolated from other volcanoes in the area, but also because it is located nowhere near the Maria, where volcanoes are usually found. Also, on the far side, we find the Jackson crater, which, like the Tycho crater on the near side, has an extensive and complex ray system. In fact, this crater is often considered to be like a twin to Tycho. Finally, the Tsiolkovsky crater stands out as an excellent example of a far-side crater filled with a sea of ancient lava, known as a mare. It is particularly interesting to scientists and other observers because of its isolation from other similar craters, as well as its beautiful central peak. As we continue to study the Moon, our understanding of it improves, giving us new insights not only into how it has evolved over time, but also how other rocky planets in our solar system have come to look the way they do. With new missions, new instruments, and new technologies, we will continue to improve our knowledge of the Moon and better understand the history of our solar system.
awesome. Okay, sorry, I have to go back. The biggest single point that you should get from the movie is that, even though, there are debates about, whether, Pluto is a planet or, whether various bodies are planets or dwarf planets or whatever, but at least as a scientist, we kind of lump all of the large bodies in the solar system together as just worlds that we can study. And so what Stephanie said about, using the moon to learn more about other rocky planets is just totally apropos. I mean, we treat the moon with the same amount of respect that we give the other rocky planets because they're just examples of different ways that things can evolve and different physical processes that have operated throughout the history of the solar system. Okay, so I know I'm probably running a bit late because of technical difficulties, so I'll try to be quick on this. But much of this was in the movie, but the main hypothesis, which came out ultimately from the Apollo results, and then numerical modeling, computer modeling, is that the moon originated in the impact of a body roughly the size of Mars. So in terms of how big it is across, the Earth is about twice as big as Mars, and Mars is about twice as big as as the Moon. Excuse me. So imagine that this is like, imagine this is an extra planet that was floating around the inner solar system for tens of millions of years, and it ultimately hit the Earth and made a huge splat. Okay, so basically what would have happened is that a lot of debris would have been splashed off in the impact. And, here, let me go back a second. So essentially what you would have ended up with the Earth being surrounded by a giant version of Saturn's rings, namely a huge collection of particles, which, anything from dust all the way up to small moons. Except Saturn's rings are balls of ice, and when the moon was forming, this giant ring around the Earth would basically be a molten rocky ring. Okay, so what we believe happens is that you have this shows this sort of ring that the Earth is surrounded by, and moons start forming in it, and then here's one, here's another one, and then they coagulate. They gradually collide with each other and form the moon that we know and love. Okay, and this is thought to have happened about 4.5 billion years ago. So this is what it looked like. Shortly, meaning probably only 100 or 1,000 years after the moon forming the impact. So the moon here is mostly formed, but it's still embedded in a ring, so it's still gathering some material. Okay, so the early solar system was much more packed with small bodies than it is now. So the moon would have been bombarded by other things for quite a while, for 100 or 200 million years. And, and it's perhaps in one of these impacts, maybe 4.3 billion years ago, that the South Pole Aitken Basin was formed, the one near the South Pole of the moon, which was mentioned in the movie. In fact, there's so many impacts that it ends up essentially melting the whole top of the moon, creating something called a magma ocean. And the main evidence for this is the chemical composition of the moon. Okay, so here's a little art of conception of what the very early moon may have looked like. So this would be, so there was some solid surface, but a lot of magma. Okay, the evidence for this is actually the moon rocks that the astronauts brought back. You know, feldspar is a common rock on Earth. A lot of the moon, especially the lunar highlands, the brighter part, is a type of rock called anorthosite, which is this calcium aluminum silicate here. And basically what was shown, in fact, very soon after the moon landings, I just looked this up yesterday, and it was in the first slew of papers that came out in 1970, the year after the first moon landing. This idea of a lunar magma ocean was proposed, and basically this anorthosite is like the light material that would have floated up to the top of the magma ocean and then solidified. Okay, so sorry, I don't know what happened to this clock here, but anyway, for some period of time, the moon would have been struck by asteroids and comets, as still happens today, but at a much slower rate. Something I added to this presentation, because it's near and dear to my heart, is that there may have been actually a pause in the impact rate for hundreds of millions of years, because work by my colleagues here in Boulder and other places came up with something called the Nice model, because a lot of the work was done when my colleague Cal Levison was on sabbatical in Nice, France. And there's actually a lot of evidence that in the early solar system, the giant planets, namely Jupiter, Saturn, Uranus, and Neptune, were a lot closer together than they are now. So basically, these are all on the same scale. So this is what we think the solar system looked like early on. This doesn't show Mercury, Venus, Earth, Moon, or Mars. This just shows the orbits of Jupiter, Saturn, Uranus, and Neptune. So the point is that because of the way the orbits evolved, the planets themselves actually probably destabilized the Kuiper Belt, which is this region beyond the giant planets where Pluto lives today, and other Eris, which is another similar-sized Kuiper Belt object. And so all of these little white dots, which represent essentially small bodies that were present in the early solar system, got flung all across, hither and to. So there would have been heavy bombardment of all the planets and moons. And sometime later, you would have been left with the planets in bigger orbits, and most of these small bodies gone, mostly ejected from the solar system actually by Jupiter, but still some number of them remain until today. And we believe actually that they are the source of one of the types of comets we see that come by sometimes. Okay. In this period, about 3.8 to 3.9 billion years ago, some of the biggest craters after South Pole Aitken formed, including Imbrium, which is the biggest crater that you can see easily on the near side of the moon, and one called Imbrium, which is near the edge of the moon, on the west side, on the west side of the moon. And I guess because LPI is in Texas, Texas has been superimposed on this view graph. But you can see these are really big craters. We're talking, 1,000 kilometers or so across. These impacts, basically, they make a real mess of the crust of the moon. So even after it's solidified, which happens pretty quickly, the impacts can melt small amounts of rock and jumble up pre-existing rock types to make these type of rocks called breccias, which you can see are kind of an agglomeration of different types of rock. The dark Maria formed somewhat later, starting mostly about 3 billion years ago and ending about 1 billion years ago. And the point is that, I mean, this doesn't happen right after the impact. What happens is that the impacts form craters, and so the moon was warmer earlier on. It was more geologically active than it is now. So there was some lava on the moon, and it tended to fill in the low spots, meaning the big craters, which are called basins. And this just shows an example of, lava today in Hawaii. And the same sort of thing would have happened on the moon. Okay, and the lava extruded from the moon starting about 3 billion years ago would have formed rocks like basalt, which again is a common rock on Earth, formed from volcanic lava. Okay, so the moon is not very active right now. There's still the moon actually has some little quakes, moonquakes. But the moon is not, very active now, and that's mainly because it's smaller than the Earth. So originally it was warm, both because of the heat of the impact that formed it and the subsequent big impacts and radioactivity inside it. But just because it has a smaller size, heat leaks out faster than it does for the Earth. So the Earth is still a lot more active than the moon is. Okay, so this just summarizes what we think the very early moon looked like after it solidified, what it looked like after the Maria formed, after the lava flows occurred, and what it looks like now. And I should mention, probably all craters, or most craters that form on the moon, form these rays, which you can see, but they tend to be erased for the older craters, so you can only see them on the younger craters. Okay, all right. Okay, I believe you're going to have another webinar on this next month, but I just wanted to mention, if you were paying close attention, you might wonder, well, the stuff we've shown, had the moon really close to the Earth, and now the moon is pretty far away from the Earth. And how did that happen? And it turns out that the Apollo astronauts actually put these things called laser retroreflectors on the moon. They're basically mirrors. And to this day, astronomers shine lasers at the moon. A very small fraction, but a detectable amount, comes back from these laser retroreflectors. And it can be detected that the moon is moving away by about 3.8 centimeters a year, which turns out to be, that's an inch and a half, but if you extrapolate that back, that means the moon was very close to the Earth billions of years ago, and so it all works out. And this is actually due to tides, the tides that the moon causes in the ocean and actually in the solid Earth, and hopefully you'll hear more about that next month. Okay, so the current moon, it is pretty quiet, but you do see things happen. This is a little video made from a small telescope on Earth showing that a small object hit the moon in 2005, made a little flash when it hit, and then you can't see it in this Earth-based image, but there should be a little crater here. So it's estimated to be something like 9 feet across. Okay, and perhaps a better example, or at least an example where you can see the crater, is here's a picture of a region of the moon taken by Apollo 15. Here's the same region of the moon taken in 2009 by LRO, the mission that I mentioned earlier. And overall, the image looks a little bit sharper because, we have better technology now. We have CCDs instead of photography. We have the same type of technology that you have in a digital camera. But there's this new crater here, which again is very small. But you can see that, this crater was not here 38 years earlier. So this is a small crater that formed, since Apollo. Okay, and then finally, as shown in the movie, You know, LRO has really amazing resolution. So this is Apollo 12. I think they did this for all the Apollo landing sites. And so you actually can see, you know, the tracks where the astronauts roved around the moon. So people really did land on the moon. It wasn't a Hollywood production or a conspiracy or something like that. Okay, so that's about it. I just wanted to say that, you know, as a kid, I was very inspired by 2001: A Space Odyssey, the film, and in that movie, you know, you might remember if you've seen it, that early in the film, some people go to the moon via Pan Am, which is an airline that no longer exists, unfortunately, but it was very routine in the movie, and I really thought when I was a kid that probably I would get to visit the moon in my lifetime, and it's not looking too good for that, but some NASA engineers are still thinking about how you can do this and make it routine to go to the moon. For scientific purposes, you don't need people as much, but we definitely need a busy program of lunar probes. And I just wanted to close with this, which is a picture taken from Mars, in fact by, you know, not the spacecraft that just got there, but Mars Reconnaissance Orbiter, which is sort of the Mars version of Lunar Reconnaissance Orbiter. And so this picture of the Earth and Moon was taken from Mars, and I asked some of my friends yesterday what was their favorite picture of the Earth and the Moon taken from space, and this seemed to be the winner, so I thought I'd show this to you. But the Moon has a lot to tell us about, you know, the history of the Earth and the way in which the planets form, so I hope we will continue studying it in future years. And that's all I have to say, so I'd be happy to take your questions, and I'm sorry if I ran over a bit.
Okay, well, thank you very much, Luke. And we'll keep an eye on the chat window here for just a moment. Are there any questions that you would like to have Luke answer for you before we move on? Okay, it looks like we have one coming in,
Okay?
perhaps.
I'm also happy to take questions, you know, after the webinar if people think of things later. I'm happy to answer questions by email or whatever.
Okay. Yeah, that's a very generous offer, and if anyone would like to take him up on that, you feel free to send your questions to me, and I will pass them along to Luke for you, and he can get you the answers for those questions. I'll give it just another moment in case there are any before we move on. Okay, looks like I do have one question for you here. How long did it take to form the moon after the planetary body hit the moon?
Okay, yeah. So we think that it took something like 100 to 1,000 years for the moon to form. That is basically set by just the little pieces that the moon formed out of. Need some time to cool off a bit before they can really start coagulating well. But yeah, it would be very short by solar system standards. I mean, at that time, the moon still would have had this sort of liquid outer part, this magma ocean, but it achieves basically its current size and mass very quickly.
Okay, it looks like I have another question for you from Xavier. Within the advances in technology, do you feel that we will be able to learn things that might benefit us here on Earth in our lifetime?
Okay, well, I can think of I can think of a couple of things. I mean, I have to admit that, you know, I'm basically in pure science. I don't think too much about the applications, but certainly there has been talk about mining the moon for various resources. You know, if fusion technology is ever developed, which, you know, it's been sort of a long time coming, but there is something called helium-3 on the moon, which is rare on Earth. So that would be like a starting step for nuclear fusion reactors, which are probably a lot safer than fission reactors. And you know, honestly, I think, you know, it's very unlikely that the Earth will suffer a horrible impact such as the one that probably killed the dinosaurs 65 million years ago. But I do think the moon is a logical place to have a colony. And so I do hope that there is some permanent settlement on the moon in at least the next few decades, because you know, it's not good to have all our eggs in one basket. And I think, you know, just the moon is so much closer than Mars is. You know, even at its closest, Mars is about 100 times further away than the moon is. So I know a lot of people are excited about Mars now, but, you know, settling Mars is just so much harder than the moon that I think we ought to kind of take baby steps and try settling the moon first and really see how people deal with that first. Because, you know, if there's an emergency, you can get back in a few days, and you can't do that from Mars with anything like current technology.
Okay, we have another question for you. If the moon was formed by accretion of particles, why weren't the particles destroyed when they impacted each other?
Yeah, that's a really good question that I meant to actually say that. What happens when solid bodies collide depends on basically how fast they're going and sort of compared to their escape velocity. And the point is that the collisions between these objects were slow enough that basically they stuck together, which is what happens in the relatively low-speed collisions. At the opposite extreme, in the asteroid belt today, you actually see cases where there are a bunch of asteroids on similar orbits, and those are thought to result from, you know, catastrophic destruction of a pre-existing asteroid. So you had a big asteroid that was just minding its own business. A smaller asteroid came around, hit it so hard that it just broke up into a bunch of chunks, and the chunks were not able to put themselves back together again because the speed of the collision was a lot faster than, you know, the gravity of the fragments is able to put back together.
Okay, I'm not seeing any other questions unless someone's coming in.
It looks like Stephanie says there was one more. Actually, what about the moon getting further from the Earth? Okay, maybe I see two questions here, but maybe I'll just try to answer them both real quickly because I know I'm running late. The main effect on the moon getting further from the Earth is that it turns out the day is getting longer. There's this thing called conservation of angular momentum, and basically all the sort of the spins of the Earth and Moon and the speed of the moon in its orbit all sort of have to add up in a certain way. And because the moon is getting further away, the Earth's spin is slowing down. So the day is getting longer, but at a very slow rate. So that's the immediate effect. In the distant future, the sun actually will affect the moon, and the moon actually may come back and strike the Earth in the very distant future. Well, I'm talking many billions of years. So that's something you may hear about next month. And finally, about moon travel by the everyday person, I hope so. I mean, if I had to guess, I'd say probably in 50 years. So probably not in my lifetime, but hopefully in some of your lifetimes. Anyway, I think I probably should quit. But thanks very much for your questions, and again, I'll answer any questions I get by email. So thank you.
Oh, and thank you, Luke. We really appreciate you taking the time to be with us today, and we enjoyed getting to hear more about the formation of the moon and how it's evolved over time.
It's a pleasure. Thank you very much.
Thank you.
Okay, bye-bye.
So I just wanted to make a comment real quick and let you know that, yes, we will have a copy of the PowerPoint slides from today available for a small fee. And we'll make sure that you get that information following the webinar. Just so you know, the webinar will also be archived, and so we'll have links to where you'll be able to access that if desired as well. So with that in mind, now we get to move on. We have a nice foundation now in the formation and evolution of our moon. So the next thing we want to do is, if I can get my slide to advance. There we go. We want to get our hands dirty and start getting into the Marvel Moon activities. And so we're going to get in and do some of these hands-on activities. And we already got a little bit of a start with the first one. And the first one is called Wham Moon, and it is about the formation of the moon. And so for this activity, I would ask if you have your supplies with you, grab your Play-Doh again. We're going to be using it to model this formation story. And so when you do this with the kids, there will be pages in the module that you can print out that contain the story of the birth of the moon or the formation of the moon that you'll be able to walk them through. And as they're doing that, and as we're going to do in just a moment, they'll work in teams to help model that story and enact it through the Play-Doh. So I see that we are getting our Play-Doh ready. We're going to switch over. Andy's going to help us to demonstrate this. But first we want to think about before the moon formed, the moonless Earth. We'll go way back in time to about 4.5 billion years ago and think about what the Earth was like at that time. And of course, at that time, the Earth was a much different place. It wasn't the lush green and blue, beautiful place that we know today. It was newly formed, which means it was very hot. It was red and glowing. And so very different than what we're used to. Now, about 4.5 billion years ago, let's click this again, sorry. There was also another small planet orbiting the sun in the same region as the Earth, like we just learned with Luke. And so we have our Play-Doh Earth here, and what we're going to do next is we're going to create a small planet out of a different color of Play-Doh. We'll want to make sure that we create the smaller planet to be about half the size of the Earth, like Luke told us in just a little while ago. So here we go. We have our Earth, and we have our small planet. Now, as the small planet was orbiting in the region near to the Earth, at some point it collided, and there was a violent impact between this small planet and the Earth. Now, when the small planet hit the Earth, it didn't hit it dead on or dead center. It hit to the side a little bit, kind of a glancing blow to the Earth, as Andy is going to kind of show in just a moment. And this glancing blow had a couple of consequences. One is that it sent debris, or pieces of the small planet and pieces of the outer layers of the Earth, out into space. And so he's making those small pieces now. Please follow along with your Play-Doh. Make sure to get some debris from both the small planet and from the Earth. And you can scatter those around the edges of your plate. Okay, and so this small planet basically shattered and disintegrated into the Earth. And so pieces of it were flung out into space along with the pieces of the outer layers of the Earth. The rest of that planet was diving into the interior of the Earth, and it was merging with the Earth then. And so I think we've got enough debris. Andy doesn't want to stop. That's okay. Okay, so we've got our debris. Now we're going to get our Earth and our small planet again. Now remember that they just collided. They sent this debris flying into space around the Earth, and that rest of that small planet plunged into the interior of the Earth, merging with it. So Andy's going to simulate that now with the Play-Doh. You'll see he's stretching it a bit to make this work. So here comes the small planet crashing into the Earth at 25,000 miles per hour. And merging with the interior of the Earth. Okay, so now we're going to slide our debris around to the edges of the plate so it's around the outside of our Earth. Because as Luke mentioned, after this, we were left with a disk of debris or a ring of debris surrounding the Earth. And so what happened next was that process of accretion that he mentioned, which means that these pieces of debris started to collide with each other. Sometimes when they would collide, they would stick together and accrete. Sometimes they would hit and bounce apart. But over a period of about 100 to 1,000 years, like he mentioned, we're going to move these around with our hand and get them to accrete together, forming them into an early moon. So this process was going on around the Earth. These pieces, we'll push a little harder, get it to accrete together until we have our small new moon. Okay, so now if we take a look at both our moon next to our Earth, notice the moon has material from both the Earth and the small planet. It has some of the outer layers of the Earth that were accreted into that new moon and parts of that small planet. But if we spin around the Earth a little bit under the camera, you'll see that we don't really see any evidence of that small planet on the outside of the Earth. Well, except for where Andy had a spot there. But ignore that. So we don't see evidence of the small planet on Earth today, but there are pieces of it still within the moon. Okay, so we were able to model this formation process. You would do this as well with the kids. And then you could conclude by looking at your comic book page with them. For this activity, the comic book page is actually a comic strip where they would get to draw in then their Earth and their moon and then put together the story of how that moon formed to take home and share with their family and to help keep in their mind how that whole process happened. Okay, so we're going to switch back to me in just a moment here. And so now we've gone through an activity where we're able to go through the story of the formation of the moon with the children and to model it with the Play-Doh. The next activity we want to look at is going to create another model, but a little more detailed one, and even better, it's edible. So this is one that we can make out of everyday food materials, and we're going to make an edible Earth and an edible moon. So first of all, we're going to consider the Earth. And so I have a question for all of you. Please use your chat box. What is it like on the inside of the Earth? Are there layers? Can you name any of those? While you do that, Andy's going to get out the edible Earth that we've made ahead of time. Okay, I see layers, core, mantle, crust, other question mark. Okay, good. That sounds like a good start. Layers, center is hot. The core, the mantle, and the crust. Okay, excellent. So thinking about what the inside of our Earth looks like. Now I'm going to switch over here to the camera. You'll see our edible Earth. We made this using 4 full Rice Krispie treats, a large marshmallow, some red icing, and some colored sprinkles, blue and green, as well as some chocolate chips. So there's the Rice Krispie treat. So in order to make this Earth, you actually need 4 Rice Krispie treats plus another 3/4 of another Rice Krispie treat. Now Andy is going to cut our Earth in half so that we can look inside and discover our layers. So you'd work with the children to build this or create this edible Earth. And now we can cut it open and take a look and see what we find. So, looking at this, we have modeled the different layers within the inside of our Earth. And Andy's going to kind of just point with the knife here, but on the very center, you'll see the large marshmallow that we used. You can also use a donut hole for this. This is our solid metallic inner core, made mostly of iron. Surrounding that, you'll see some kind of pinkish looking stuff. It should be surrounding all of it. It's actually red icing. That is our liquid or molten outer core. Beyond that, we now Next, you'll notice the Rice Krispie treat area. This is kind of the intermediate area. This is the mantle of the Earth. The mantle is a solid, but it's a ductile solid, which means that although it is solid, it is able to flow and move. And then finally, the outside. Maybe we'll have him turn one a little bit so we can see it. On the outside, then, we have our sprinkles, the blue and the green, and that is, of course, the Earth's crust. So really quick, can someone tell us what are the two types of crust that we have here on the outside of the Earth? There you go, we flipped one over for you. Anybody want to share what type of crust do we have on the Earth? There's two types. Okay, well, if you look, you notice we have the blue and the green sprinkles showing the two types of crust. He's zooming in a bit for you. There you go. You can see it a little bit better. Ah, I see land and water. Excellent. Yes. So the green sprinkles are representing our continental crust. That would be the land that we all are used to living on. And then the blue sprinkles are showing our oceanic crust, the crust beneath the oceans. Excellent. Okay. So here is our Earth and the different layers. Now let's start thinking about the moon. Does the moon have layers? Okay. Not seeing any responses come in quite yet, but we're going to keep moving anyway. Of course, the answer is yes, the moon does have layers. And so we're going to create our edible moon next. In the messages I sent you prior to the webinar, I gave you a list of materials. If you've collected those, you can follow along with us right now and make the edible moon along with us. And for this, Andy's going to show we have our Rice Krispie treat, which we have cut, and noticed we've taken off 1/4 of it. For the moon, we just need this 1/4 of the Rice Krispie treat. He's going to flatten that just a little bit. Okay, next he's going to take a red cinnamon candy, or in this case it's actually our Red Hots, and he's going to press that into the center. And then very gently wrap the Rice Krispie treat around the cinnamon candy, creating a ball. And there we go. Okay, so we have it started. The next thing we're going to do is he's going to show you a baggie of a powdered mixture we've put together. And this mixture, sorry, I'll get to our recipe here. This mixture is made out of 1 teaspoon of hot cocoa mix and 1 teaspoon of powdered sugar. We shook that up inside the baggie to make a nice kind of grayish brown mixture. And now we're going to stick our Rice Krispie moon into that bag with the powdered mixture. And then roll it kind of around in that. And make sure to coat the outside of your Rice Krispie treat with that powder. So roll it around, move it. He's moving it a little bit. Okay, you can press it on there a little bit if you like. And once it's nice and coated, we'll go ahead and remove it from the bag, set that aside, and we'll finish up with our moon. Okay, so there we go. Now the next couple last steps for our moon. Andy's going to take his fingers and make lots and lots of nice craters on the outside of our moon, because we all know the moon has lots of craters. Okay, that looks fairly good. Okay, so and then the last step, what we'll do is we'll take 3 or 4 regular-sized chocolate chips, and you're going to press them tip down into your moon. And these are creating those dark-colored areas on the moon that we see that are called maria. I see some of you are making the edible moon. Excellent. Glad to see you following along. Also notice a comment that maybe small children would need help with the Rice Krispie treat. Definitely, you might want to have some extra volunteers on hand for that. Okay, so here we go. Here's our edible moon, and now Andy's going to take the knife and cut that in half, and we're going to compare it to our edible earth. Of course, with the red hot in there, or the cinnamon candy, you probably have to kind of go around it a bit to get it to open up. So cut carefully. And actually, while we're opening up our moon, I would invite all of you who made an edible moon to go ahead and please enjoy it and eat it. That's one of the better parts. Okay, so here we go. He's zoomed in on our moon. It's not completely round, but that's okay. We get the idea. And next we're going to set our half of our Earth by it as well. I'd like to compare the two. But while he's getting that, if you look at our edible moon on the inside, you'll notice the different layers. And for our moon, we notice we have a core represented by the red hot candy or the cinnamon candy. That is a solid metallic core surrounded by the area of Rice Krispie treat, which is representing the mantle of the moon. And then on the outside, we have that powdered mixture, which of course is the crust. So looking at the two, if you see some differences, this would be something you'd want to discuss with the children and see what they notice about the difference between the inside of the moon and the Earth, how they have similar layers, but the Earth has that liquid outer core, which the moon does not have, as well as maybe the size proportions. If you look at the moon, you notice that the mantle is much thicker compared to the core. The core is much smaller. And if we think about how the moon formed and the fact that only the outer layers of the Earth were blown off into space as debris, then that should start to make some sense. Okay, so how were your Rice Krispie treats? How were your edible moons? Did they taste okay? Excellent. I'm seeing lots of fun. Glad that you enjoyed that one. Some of you are enjoying it a lot. Excellent. Okay. So of course, just like all the other activities in the module, we do have a comic book page for this activity as well. And so at the conclusion of creating these edible models and then enjoying them, the children can take a moment to capture what they've created and draw their Earth and their moon and the different layers and label it. And so they can take that back with them to combine into a full comic book later. Okay, I saw a comment there, but okay. So moving on, we have made quite the progress. We've gone through and kind of modeled the story of the formation of the moon. We just created a more detailed model of what the inside of the moon is like. And so the next activity we're going to do with you is going to look at how that structure formed. So how we got those layers on the inside of the moon. And so this activity is called Infant Moon, Moon Mix. The moon was still in its infancy. And if you'll recall from Dr. Luke Doan's presentation, after the moon formed and was being impacted by all these large impactors, if you think of clapping your hands, produced a lot of heat and a lot of energy was released. So the moon was a very hot place, and as he mentioned, they believe the whole outside of the moon was actually a magma ocean. It was molten rock. And so over time, this slowly was able to cool, and as it cooled, the different minerals and materials within that magma started to crystallize, and as that happened, a process called differentiation occurred. Differentiation means that as these different minerals were crystallizing and kind of settling out, the more dense materials like the metallic iron would sink to the interior of the moon, forming that solid metallic core. And the lighter or the less dense materials would rise and to form that lighter crust. And most of those are made out of a silicate. Okay, so for this activity, we're going to use some different craft materials to recreate this process of differentiation. And so we're going to have a small water bottle that we'll use for this. We'll go ahead and start showing some of those materials. I believe we'll want to tilt our camera here for a moment, or I can hold it up. Okay, so here I have a small water bottle, and this size here seems to work pretty nicely for us. We measured it. If you measured to a nice fill line, it'd be about 10 centimeters. You could go ahead and pre-mark a fill line, as well as marks for the layers if you choose to. If you were going to do that, you could mark about 2 centimeters for the bottom for the core, and about 1/4 centimeter from the top fill line for the crust. So there's our little bottle. Okay, thank you. And as part of this, we're going to be using one of a variety of different liquids. We have kind of 3 main liquids we'll consider for this. Mostly either water, vegetable oil, or corn syrup seem to work very well. And then we have other random materials that we'll let the children test and try out in order to create the other layers, the core and the crust. So I'm going to hand this back. We're going to flip over to our camera and show you some materials that we recommend for this activity. And as we zoom out, you'll notice we had sequins on there. Sequins work nicely. Straws can be cut up into small pieces. Coffee stirrers especially work well. You'll notice pieces of sponge. There are small wooden beads on there. We also have some dried beans. Some aquarium gravel is nice. And we have some peppercorns in the corner there, around the edge. So these would just be some ideas. And if you go into the activity description online, there will be a variety of other materials listed that you could test and try out. So the first thing you want to do, let the kids have a cup of the liquids that they could possibly be choosing from. So you'd have a cup of water or vegetable oil or corn syrup, and let them start testing which materials float and which ones sink. Because of course, for the dense core, you need something that sinks, and for the light crust, you need something that floats. So over the process of them doing that, also encourage them to make predictions, which we're going to do right now, real quick. We have a couple of polls we're going to bring up, and we want you to predict which of these materials would model the crust the best. Go ahead and vote. Which of these materials listed on the voting box do you think would model the crust the best? Seeing some votes for sponge pieces and sequins. Give you just a moment. Oh, I think sequins are getting the largest vote right now. Don't be afraid to vote. Okay, I think we've gotten quite a few responses in. Looks like sequins is still our winner. It looks like sponge pieces and straw pieces are pretty highly recommended, or the buttons as well. Excellent. Okay, well, let's bring up the next poll. So that was the crust. The next thing we want you to vote on is the core. Which materials do you think would model the core the best? Okay, I'm seeing votes for aquarium gravel and a couple for pancake syrup and sponge pieces and dried beans. Aquarium gravel is our winner, I think. It seems to be the most popular by far. Excellent. Okay, so children will get a chance to test these out, and then what you will do is actually make your moon mix bottle. So you see on our comic strip page here that we've kind of listed some different materials that could be used for different parts of this model for differentiation. For the crust, we can recommend using the dried beans, oil, sponge pieces, or straw pieces. For the mantle, water or corn syrup work well. For the core, things that sink, like aquarium gravel, buttons, pancake syrup, or sequins would be nice. I will mention, though, you want them to test these thoroughly because there will be some items that may float on top of water initially, but if you were to push them down and release them, they may sink. So always have the kids be nice and thorough as they're testing their materials. Now we have a couple of bottles we've pre-made to show you just really quickly. And the first one we have here, number one, we're going to tilt our camera up, I believe, in just a moment. Okay, so you can see he has it up. He has it on there right now. There we go. He flipped it, and the material switched. Now you can see this one. We have the wood beads and the aquarium gravel. Let me make one adjustment really quickly. There we go. Helps if it's not showing it upside down. So there we go. So if he'll flip it slowly one more time, we got the water for the mantle, the aquarium gravel for the core, and of course the wood beads for our crust. So one more time really quickly, I just want to show you. The water makes it move pretty fast, but we can see how those things are differentiating themselves, much like the process we're describing for the moon. Okay, so we have another one we want to show. Since the water does tend to let things move pretty quickly, you may want to use something a little thicker for your mantle. In this case, I believe we have vegetable oil, and we've used gravel and pony beads for the bottle. This is a little bigger bottle. And so in order for the children to really test out their differentiation process, Andy's going to shake this up. We're going to shake it up in front of the camera. So here we go. We'll shake it up. Here's our molten magma ocean that has not been differentiated yet. And now he will let it hold still and settle. And there you go. We see the formation of the crust, the mantle, and the core. Excellent. Okay, and one more example we want to show you really quickly is one that is a little bit of an unexpected outcome, because in this one we've used corn syrup. So the crust item we're using are dried beans, which normally would sink in water, but as you'll see in the corn syrup, they actually float. And then we have our gravel, again, for the core. So you can see he shook it up. And in this case, the items are going to differentiate very slowly, kind of like a slow lava lamp moving up there. So you'll see the crust and the core slowly forming and going into their positions and modeling that process of differentiation. Okay. Thank you, Andy. We appreciate your help showing those items. So are there any questions about this activity before we move on? A lot of flexibility as far as the items you use, so you should be able to find something pretty inexpensive and handy. I see we do have an incoming question, so we'll give that just a moment. Okay, I guess we're good to proceed. So next up, actually, I'm going to turn over the stage to Andy, and he's going to start telling you about some other activities we have in our module. And the next one is taking us from the formation or birth of the moon through its infancy to more of its kid stage. So really quickly before we do that, I noticed we just had a question come in. What age is this appropriate for? That's an excellent question. I'm glad somebody asked that. Actually, all of the activities in this module are appropriate for children ages 8 to 13. We really don't recommend that you use it for younger. These concepts could be confused or produce misconceptions in younger children. So we want to make sure that we use them in an age-appropriate way. But children 8 to 13 or even older would be more than appropriate for these sorts of activities. So, thank you for that question. That was excellent. And as I mentioned, I'm going to turn it over to Andy, and we're going to move on to the next activity.
Okay, we've got to adjust the camera first. There we go. Got him a little bit taller. All right, thank you. Whoa. There we go. All right. Hi, webinar world. Thank you, Eve. So with the differentiation bottles, we just talked about the Earth, or the Moon, at its very young stage. When our Moon was born and formed, we separate out into layers. The the crust is starting to solidify, it's starting to harden to become a rock. So this next activity we have called SPLAT is going to help us demonstrate the late heavy bombardment. So this period in the moon's history when it experienced this intense pummeling by asteroids and comets. Well, not just the moon, all the planets in the solar system did, but the record of this event is best preserved on the moon. And that's evident from the mini craters and the mini sized craters that you see on it. All right, so for this activity, we're basically going to be modeling the impact cratering process, but without creating a crater, so to speak. We'll explain what that means. So this is probably one of the more fun activities in the module. Not that they're not all fun, but this is certainly a popular one. We need a balloon, a water balloon to be exact. So if we could switch over to, there we go. So you can see on the PowerPoint slide, there's a balloon there. It's about 2.5 inches, and that's the short dimension. So our balloon here is about the same, maybe 3 inches. About the same, maybe 3 inches wide. So that's about the size we're looking for. You don't want to pop the balloon. You want to make it too big. All right, so we need a water balloon filled with water. It's about 2.5 or 3 inches. Okay. So this is our impactor. This is what we're going to toss or drop on the ground. This is the incoming asteroid or the incoming comet that's going to hit the surface of the moon. And when we do that, you can imagine what's going to happen. You'll get a nice big splat or a splash on the surface. This is just the sidewalk outside here at LPI. And then what you want to do is measure the width of that splat, the splash width. And don't include the rays. You'll see those little rays of water droplets going out away from the middle. Don't count those or don't include those in your measurement. Just measure the width of the round splash or splat. Okay. And there again, you see that picture on the left of Orientale Basin. And yes, it is in there as compared to Texas, because most of our audiences are in Texas, so that's a nice comparison for them. This is a very big splat on the surface of the moon. So in our previous slide, we had a balloon that was about 2.5 inches wide, and this was 44 inches wide. And so if we take that ratio, in other words, if we take the width of the crater, okay, there's a splash in this case, and divide it by the size of the balloon, or our impactor, we'll get a number. Okay? And when we do that for this specific example we have here in our images, and this again, this is a page from the comic book, so this is can show you the children how to do this. That's very, very simple math. So when we take this ratio, this 44 inches of the crater or splash width, and divide that by the 2.5 inches of the impactor of the balloon, we get about 17.6. Right? And that's nice because that falls within a range that scientists estimate that when an asteroid or comet hits the moon or hits the planetary surface, the resulting crater is anywhere between 10 and 20 times the size of that impactor. Okay? So this ratio we have here fits in perfectly within that size range. So you should get similar results as well. No matter what size your balloon, you'll get a splash width somewhere between 10 and 20 times the size. So out of curiosity, does that surprise anybody that the resulting crater is at least 10 times the size of the object that hit it, sometimes even as big as 20 times the size? Anybody out there that surprised you? Well, it turns out there's a lot of energy. We won't go into that. There's a lot of energy involved in these impact processes. Lots and lots of energy gets released, and lots of material gets thrown out to form these craters. All right. So now we can just kind of continue to move on into the aging of the moon, so to speak. We're kind of past that impact period and are now moving into the period with volcanism. So we had lava erupting from below the surface up onto the surface of the moon, creating the mare, the dark spots that we see on the moon. The next activity, moon ooze, is used to model that idea. We see here on this slide, we saw it in Luke's presentation. There's Mare Imbrium on the left, and just the southwest corner of that on the right side image there. And that dark rock, that hardened or solidified lava called basalt, We have a picture of it. If we can switch over to the, there we go. Now this, of course, this is a basalt rock from the Earth, not from the moon. We wouldn't be able to hold this if it was from the moon. It'd be illegal. So we have a piece of the Earth that we're holding. This is the exact same type of rock you'll find in Hawaii. The Hawaiian Islands are made of this. The ocean floor is made of this type of rock, as well as the Galapagos Islands. You may have heard of those before. So this is an example of basalt rock. This is the same type of rock that you see in the mare on the moon. I saw that question. Well, because the moon rocks that we have were brought back by the Apollo astronauts. They're brought back by the government, so you can't have those things in your possession. That's yeah. That's sorry. All right, so let's go to the our back to our Elmo here and look at the activity. So we'll start off with, we have two plates, this larger plate and a smaller plate. The larger plate could be modeling like the crater or maybe even, or I'm sorry, like the subsurface below the surface of the moon. These smaller plates will be kind of the surface of the moon where the lava will come up through. You can see we put these slits in the plate to show the cracks or the fractures that were in the craters as a result of the cratering in the crater floors. So we'll show you how this will ooze up. We've got some water that's just colored with red food coloring to represent the lava. So let's put some of that in the plate there. You can see. Okay, very good. So there's our lava underneath the surface of the moon. It's hot. It's liquidy, viscous. All right. So we'll place that top plate on there with the cracks. We'll see it oozing. You have to, of course, press down on that top plate, but once you do that, you'll see that lava start oozing out of those cracks, start filling in that crater. So just like we saw, or we didn't see, but just like we see now the result of lava flowing out and filling in these basins, these lower lying areas on the moon. So that's our model mare, or moon ooze, the volcanism, modeling volcanism of lava coming out on the moon's surface from about 3 billion years ago till about 1 billion years ago. Again, so in the comic, children can draw what they just saw happening, put it out on paper, and then check on the side there, where did this come from? How did this lava come from? So it oozed out from underneath the surface in these cracks, like we modeled here. There's also a little like volcanic features where lava kind of was spit out, like you think of volcanism in generally. So those two ways are ways that lava got to the surface of the moon. All right, before we go to the next one, I just want to look at these two pictures real quick. The pictures of the surface of the moon. And what do you notice right away, a big difference between the two of those pictures? What do you notice about the two? Comparing one to the other, what do you notice? One is smoother, one appears much more smoother. Wide in number of craters, okay. More contours, okay, or more craters in the top picture, right. So the bottom picture is definitely smoother with much fewer craters than the top surfaces you see on top. And that's very important in planetary science, particularly in lunar science, that the number of craters you see on a surface on the moon is very important. It tells you something about the age of the moon, or sorry, about the age of that particular surface. So in these two pictures, we can make a general statement about the age of the surface on the top picture versus the age on the surface on the bottom picture. And the next activity is going to help us illustrate that. Okay, this is the Moon's Long History Impact Painting. This one also is pretty fun as well. This one, you'll need, go ahead and switch over. There we go. Okay, so you'll see we need cotton balls and 3 different paint colors. Particularly washable type paint, probably best. And then these targets, which you can see on there on the PowerPoint slide. There's a target with a bullseye in the middle. Of course, you want a trash bag or something to put underneath this, because as you can imagine, what we might be doing with this, you might want to protect the floor. All right, so with these 3 different paint colors, we're going to, okay? So what we could do is we'll start off, like you see here in this slide, one target, we'll say 20 seconds on top of it. And then what you want to do is take each color, dip the cotton ball in the color. You want to get quite a bit of paint on the cotton ball. And then they're gonna throw the cotton ball with the paint at the target. You want to try to hit that bullseye. And you're going to do this with each color for 20 seconds apiece. So 20 seconds with the yellow, 20 seconds with the red, 20 seconds with the brown. For all 3 colors, each one gets 20 seconds. And again, make sure you goop it up pretty good with that paint so you get a good impression on the target. Okay. So in this example, we did 3 colors, 20 seconds each. So for a total of 1 minute, you'll be throwing them. And here's the result in an example that we did with these 3 different colors. Here's what our resulting surface looks like. This is a model of what a surface of the moon could look like after being pummeled by paint for a minute. So it's pretty messy. Lots of different colors on there. Can anybody guess from this picture what was the first color that was thrown? Got red and yellow. Yellow, red. Okay. Yellow. Okay. So those are pink. Well, it's a nice color. We didn't have pink, but I can see where you got that from. It actually was red. Red was the first one, which you can probably tell. For example, you can definitely tell it was before the brown. There's some cases where the brown is laying on top of the red, okay? And then you can see other cases where, especially kind of there towards the left, between 2 brown spots, you can see red. You can see some yellow on top, a little yellow splash on top of the red. So we definitely know that the yellow was after the red. So there we go. Very good. All right. So that's after 1 minute. That's giving each color 20 seconds. Okay. Then we'll do the same thing and repeat it with a different target, but you're going to throw each color for just 5 seconds. So after throwing each color for 5 seconds, there's that result there. Okay, so that's just throwing our impactors at the surface for 15 seconds total. So if we compare those two, A on the left side, that is for throwing each color for 20 seconds. On the lower right, on B, that's throwing each color for 5 seconds. Now, the nice thing about how we can use craters, like I mentioned, the number of craters you see is important, is because the number of craters on the surface give you an idea of its age. So the more craters you see on the surface, the older that surface is. So looking at these 2 pictures, A and B, which surface would you say is older, A or B? Seeing some A's. Okay, looks like we got a lot of A's. Very good. Yeah, that's the point. The more craters you see on the surface, the older that surface is. So when we looked at these 2 pictures, yeah, there we go, look at that. So we looked at these 2 pictures at the beginning. The one on top had more craters, so it's older, and the one on the bottom had fewer craters, so it's younger. Now we can't say exactly how old they are. We just know one's older than the other. And so that's the point of this activity here. So more craters, older surface, more craters, more candles, you're older. Okay, and here it is in the comic book. They'll see the same 2, well, at least parts of the same 2 pictures that we had, and they're in the upper left and the lower right, and they're supposed to predict which one's older, which one is younger. Okay, thank you. Wow.
Well, thank you, Andy. We appreciate you taking the time to share some of those other activities. Of course, we have gone over 6 different activities from the Explore Marvel Moon module today with you. Wham Moon, Recipe for a Moon, infant moon, the moon ooze bottles, the differentiation bottles, kid moon, the splat, teen moon, the moon ooze, and then finally the moon's long history impact paintings. And of course, don't forget to make use of this customizable comic book with those. We've gotten a lot of really positive feedback about those who have done the programs and incorporated those pages. Just as a reminder, you can find all of these materials free online at the website listed above for the Explore website, Marvel Moon. And if you go there, you may also want to go check out the background information and resources for this particular module. You can find the Marvel Moon info, and you can access that facilitator background information. So if you forgot something that Dr. Luke told us, you can go back and you can read through that and freshen up on the science a little bit. A couple of other activities from that module that I just want to mention really quickly are Moon in Action, which is an observing event that you could hold. It would be great to partner with an astronomical society or club if you have one in your area, and if it is suitable for your facility or your location. An Earth-based tour of the moon handout that I had sent you previously would work nicely with this activity and at an event of that nature. Also, I wanted to mention the My Take on the Moon, and this is an activity where the children can actually create their own zine. If you're not familiar with that, it's a small 8-panel story that the children draw and add the text and create. And it's created from just one piece of normal paper that is folded into these 8 panels. And that template, of course, is in the module as well. And so your children could create a zine to create a story about the formation or the evolution of the moon and how it got to the way it is today as we see it. And you could add that to circulation at your library, and that would be a great opportunity for them to share what they've done at your Explore programs with their community and with their families. So really quickly, I just wanted to check in before we kind of wrap up the webinar with the last section, which will be our interactive programming discussion, and just make sure there weren't any last lingering questions about the formation or evolution of the moon that we haven't addressed yet. So this is your chance. If you have any other questions, please use the chat box now, and I will work to answer your questions. Andy is also on standby to help answer some of these questions. So here you go. I'm handing it over. If you have any questions, please submit them now. Of course, like we mentioned, if you're being, if you're just feeling a little shy and you want to just send us a message, we're more than happy to answer any questions that you would have after the webinar. Simply email me or email us at explore@lpi.usra.edu. And that applies to Luke Dones as well. If you have questions for our scientist, pass them along to me and I'll make sure to get him in touch with you. Okay, so I see maybe one question coming in here, so let's give this just a moment. Hopefully you've enjoyed your time with us today. Hopefully you'll find these activities and these resources useful in the programs that you offer to your community and to the children. Okay, do we have any other questions? Could you send out the link to the video for Dr. Luke? Yes, actually, if you noticed on the slide that he had for that video, I had added the web link for that particular video. And of course, like we mentioned, we'll make sure to send out and tell you how to access those PowerPoint presentations after the webinar. No. No. How did what? Okay, excellent question. We had a question come in from Hillary. How did the moon end up a perfect sphere? Because as we mentioned, all these different pieces of debris colliding together and accreting over time. As it happens, if a planetary body or a body in the solar system is large enough, the gravity involved with that large object will actually cause it to self-round over time, and so you get a pretty spherical body that forms into the moon. Why do we have just one moon? Because we only had one giant impact, perhaps, as far as I can guess. So in that giant impact, the result in our case was only one moon. But that's a great question. And I just had a comment come in over to me. And yes, if you thought about it, 4.5 billion years ago, actually there would have been many moons kind of wandering around the Earth as that process was taking place. Any other questions coming in? We had a question if you will get a certificate. I have actually more information about that. You will. It will involve completing a short survey for us, and I'll give you those details in just a little while. So I guess if there aren't any other really lingering, burning questions, we're going to go ahead and move on to our interactive programming discussion. And again, if you have any questions that pop up in your mind later, feel free to email me, and we'll make sure to answer those for you. So at this time, we are going to open up the webinar to all of you. We're going to go ahead and unmute everyone. Please, as a reminder, keep your microphone muted if you're not speaking so that we don't have disrupting background noise. But otherwise, remember we have that raise the hand feature that you can use if you'd like to use your microphone and share your lovely voice with us. We'd like to hear it. A little more personal to get the voices coming through. So this is the part where we'd like to have a talk about how would you use the materials that we've just looked at. How can you see these being used in your library or community? Do you have ideas or suggestions that you'd like to talk about with everyone else here at the webinar today? Which, by the way, are all library staff and librarians. If you want to continue to use the chat box, you may also do that as well. Yes, you can use the chat box. Says, I'm going to have an entire set of programs for families. So is that based off of these Explore module? If it is, that's excellent. We'd love to see how that goes for you. Please make sure to keep in contact with us and tell us how those programs go, and share some pictures if you get some. See if we have anybody else coming in. Okay, and other NASA programs you have looked at over the last couple of weeks. Excellent. This should fit in nicely with those. So, family night programs. Excellent. Yes, get the whole family involved in learning about the formation and evolution of our moon. Observing with NASA. Sounds like a great slogan or a great title for your program. And this will be great for families. We certainly hope so, and that's certainly what the intention was in providing these materials for you to use. This would be a good Mom's Night Out, part of STEM. Excellent. For those who don't know, STEM, of course, stands for Science, Technology, Engineering, and Math. Math and science programs. Excellent. I'm going to take these to some of your outreach programs. Excellent, yes. These would be nice in an outreach program as well. Are there any copyright issues for libraries to use these materials? No, these materials were created specifically for use by you in your libraries. I've been looking for something to do on Observe the Moon Night. I'm glad somebody mentioned that. I'm actually going to give you all a little more information about that, but international events like International Observe the Moon Night would be a great place to use these activities that we've gone over today. We're starting up a science program for homeschooled kids in our area. We're thinking 12-year-olds would be perfect. I agree. I think this program would be well suited to a homeschool workshop or program, and this certainly would be at the right level for the 12-year-olds. Can use the ideas for school visits and homeschool programs. Yes. So like we mentioned at the very beginning, these are pretty flexible and should be able to adapt them to many different types of programming. Okay, well, as it's 3 o'clock at the moment, one last thought I'll put in your minds before we wrap up is just think about your summer reading programs next year. I know that librarians are often looking for fun hands-on crafts and activities to do with those programs. I had looked it up, and it looked like some of these activities may fit into those themes, so please keep that in mind as you're planning, and may help to fill in those gaps that you need to fill. I see we had a couple more comments come in. Let's see what we got here. Will you be repeating these webinars? I'd like to recommend them to some of my colleagues. Excellent. We're glad that you've enjoyed it so much today that you want to come back. I believe we will offer more webinars in the future. We will plan to archive this one. And of course, the second part of this series will be on September 14th, and you still are able to register for that. I'll have a little more detail on that right before we're done here today. So thank you, and yes, please share this with your colleagues and your contacts and let them know about Explore and know that these resources are out there for them. Okay, well, since it is our ending time and we want to get you out of here and on your way because we know you're all very busy, I would like to finish with just a couple of resources I wanted to point you to before we leave, and the first one is NASA's Year of the Solar System. If you're not familiar with this is a program that has spanned a Martian year, which is 2 Earth years, and has been highlighting 2 years of NASA mission milestones. And so there are lots of great resources and materials on the website, which is listed boldly here for you. And if you go there, you can find the topics arranged by the big questions in planetary science, like how did the solar system form? How did it get to the way that it is we see it today? How did it evolve? And, is there life beyond Earth? So you can find topics related to those questions and organized that way. And once you get there, you'll find an area for clubs and organizations, and that would be very appropriate for informal settings like the library. And there are activities and plans that you can use in your programs. Also resources and background information that you might find very useful. And finally, I'd just like you to check out the Get Involved site on the Year of the Solar System website. If you go there, you can register your programs and events on the map that is located there. And if you do, you can receive a free pack of promotional items from Year of the Solar System while supplies last. So make sure to go check that out and spread the word about the amazing missions and discoveries that continue to go on in NASA science. And finally, the last resource I wanted to show you today is International Observe the Moon Night, or as we call it, INOM. And that will be taking place on Saturday, September 22nd. And the theme this year is Under the Same Moon. So we'll all be getting under the same moon and observing and learning and sharing our love of the moon and of space exploration. So the website is listed there. Please make sure to go and look at that. They also have a set of activities and hands-on materials that you can use in your programs. They have links to resources, and they also have a map listed there where you can, if you want to hold an INOM event, register your event. Or if you just want to go find one to attend, you can see what's near you and make sure to go check that out. So don't miss it. Get under the same moon and get out and share the love of the moon with your community as well. And finally, the exhibits. We have some, we have some traveling exhibits, relate to the moon here at LPI. If you go to the Lunar Planetary Institute website, you can find a set of library exhibits that are 3 panels on specific topics relating to the moon. And you can reserve those and bring them to your library for display and for free. So make sure to look into those resources and take advantage of all the wonderful things out there. So I apologize for going just a few minutes over, but I want to thank you all so much for attending today. We're glad that you're able to join us, and we hope that you'll keep in touch and continue to get involved with Explore. Again, don't feel free to contact us if you need to. And before you leave today, I'd ask that you please click on this link to SurveyMonkey. We have a short survey that we would like you to take. It should take you 5 minutes or less, but just give us a little bit of feedback about your experience today so we can take it back and make these webinars and these opportunities even better in the future. And if you complete that survey, once you hit the submit button, you will be directed to an online certificate where you can enter your name and print for your own pleasure your records and have to show that you've taken part in our training today. So other than that, please notice at the bottom we have our next Marvel Moon webcast titled The Moon and You. Next will be on Friday, September 14th. Same time, 1 to 3 o'clock Central Time. And we will be looking a little more at the moon and how it influences the Earth and what the Earth would be like without the moon. So the registration is still open on that if you would like, and you can contact me. Just send me an email. I can send you the direct link so you can register for that webinar. So thank you all so much. We appreciate you being with us today, and we look forward to hearing from you in the future. Have a great weekend.